K8 BYP with part 8 of amplifier design, but wanted to show you what an absolutely dead 40 meters looks like. That's the FT8, that's a digital slot, 7076. No signal level. Lightning spikes are only going to S4 to S9, just horrifyingly bad. In the previous video, we looked at the plate curves and theorized that it is absolutely a requirement that the cathode resistance be a constant, else it can't work into a pi network, a matching network. So from the plate curves, I chose conditions of 1 kV across the tube, 0.4 of an amp peak, just convenient values. That figures out to 2,500 ohms resistance P to K in the tube. That leaves a big unknown as to the most important component in the entire amplifier, and that's L sub P, the plate inductor. Beginning with 1935, as early as I can find, there's a college-level paper that incorrectly called that a choke. It is not a choke. The choke is the RFC up there by the power supply. The definition of choke, which proves that these stupid ferrite clamps on transmission lines are not chokes, is that chokes are an open circuit to RF. That plate inductor, as I've shown already, is the component that establishes the voltage drop across the plate. If it's extremely high value, there won't be any voltage swing and no amplification. None of the books I've ever seen or papers show how to calculate that value, and hams universally guess at it. After that, they're forced to vary drive levels and vary voltages and vary tuning to try to guess at proper operating conditions, and their amplifiers are usually badly distorted. With the tube being a constant resistance, there must be a varying current or the circuit does nothing. And this is where the convention of a tube being a current source comes from, and the current source is shown at the bottom, the ACI in a circle with a sine wave below it. That's in series with the plate to cathode resistance. Critical to note that the tube does not cause voltage change on the plate. And this is maybe a bit hard to wrap your mind around, but it's the inductor that causes a voltage swing. Replace the inductor with a short circuit, the tube will work, but the plate voltage will always be 2 kV, because that's the source. Replace it with an open, there's no voltage or current. So somewhere in between there, that inductor has the effect of establishing the plate voltage, and that voltage is what's coupled in a voltage-coupled amplifier to the output. To make sense of this, we have to realize that the inductor and the fixed plate resistance is an LR time constant circuit. It operates over 90 degrees, and the initial assumption I'm making is 3.7 megahertz, 75 phone band. 90 degrees of 3.7 megahertz is 68 nanoseconds. So that ratio of inductance to plate resistance has something to do with 98 nanoseconds. The basic equation that describes an inductor is VAC equals L times the differential of current over the differential of time. That's a differential equation. That dIdt doesn't seem to make a lot of sense until we consider the basic definition of inductance. Inductance is proportional to AC voltage, AC current, and time. Well, what isn't? That doesn't help a lot. Everything depends on that. Well, the basic definition of inductance is that a 1 volt inductor voltage is equal to 1 Henry times 1 ampere per second rate of current change. In the 75 meter amplifier, the current's changing at a nanosecond rate. But this is 1 second. And there's the clue as to how to crack this differential equation. That we've got to substitute in for dIdt, the rate of current change in amplifier per time, change that to a second basis per second, then multiply it by the inductance and get the voltage, but we don't know the inductance, so we don't know anything. That differential equation integrates to the form of e to the minus x, which we'll recognize as e to the minus t over tau, which is a time constant, exponential. Tau is time constant, which is L over R. So if we can find some way to solve that, we can calculate the inductance necessary to arrive at the 1 kV figure across the tube. So we set up this familiar expression, V plate to cathode, which is chosen arbitrarily to be 1,000, is 2 kV, the maximum of the power display, times the familiar quantity 1 minus e raised to the minus t over tau power, where V, p to k is 1 kV. T, the numerator of the exponent, is 1/4 cycle, 3.7 megahertz, 68 nanoseconds. In order for the circuit to only charge to partial voltage, the charging time must be less than the time constant. So T over tau is less than 1. Where tau is L over R, how much is L with 2,500 ohms resistance? Well, by inspection and by proportion, we realize that the quantity inside the parenthesis, 1 minus e raised to the minus t over tau, must be 0.5. So the 1 minus 0.5 is 0.5. 0.5 times 2 kV is 1 kV. So we isolate out the 1 minus e to the minus t over tau portion. That equals 0.5. We take the 1 out of the parenthesis, then e to the minus t over tau equals 0.5, and we know t. So by simply throwing in some educated guesses as to tau, and it has to be longer than 68 nanoseconds, we can quickly solve that exponential for the value of 1/2, and that gives us the inductance. Very simple math, but a tricky process to get there. And that's why this is guessed at. For this amplifier, for my assumptions of 1 kV, 4/10 of an amp, and so on and so forth, the inductance becomes 245 microhenry. And that's a fairly high value for typical RF amp, where it might be 100. Well, I'm very, very underloading this amp. 1 kV at 4/10 of an amp peak it may not even be half what a 3-400 is capable of. But again, I don't care about running full power. I'll be glad to get 800 watts. That'll really help. And initially building the circuit where the tube's only dissipating half or a third means that we can afford to make a few mistakes and not destroy the tube. That's all well and good, but we're still in deep trouble because we don't know the voltages across that inductor and the maximum voltage. The current is what's used to essentially rate a toroid coil, which is what I'm going to use. That doesn't really apply in an air core, but air core coils have a lot of losses to nearby components or shield walls, so I'm going to use toroids. The voltage also figures into the toroid core because it'll be rated with the voltage withstand, maybe 500 volts. That isn't much. So the wire insulation has to be rated and maybe the core taped, then worry about heat. So it's very important to know the maximum voltage across the inductor, and that's even trickier. Without being able to calculate it, we got two options. Make it too low and burn the thing up. Make it too high and make the thing much too big and too expensive. And counterintuitively enough, a larger toroid core is not the answer. Larger cores have higher loss and will tend to burn up sooner than smaller. And the reason is, as an engineer from a toroid company told me, the smaller core has less permeability, takes more copper winding, so dissipation ends up being more in the copper than in the core. So completely backwards from what you might think. The exact answer to how much is the voltage across that inductor when the tube voltage is 1 kV is found by the differential equation. di over dt, if we integrate time is linear, we just get t, which is time, which is a charge time of 68 nanoseconds. di is exponential. The current is exponential in an LR circuit with an exponential time constant. We integrate the exponential, we just get the exponential back. So in 68 nanoseconds, we find the exponential current, which we knew going in, which is 0.4 amp. To find the inductor voltage, we have question mark kV equals 245 microhenry, assuming we've calculated that correctly, and if not, we're in trouble, times the rate of change of current, 4/10 of an amp in 68 nanoseconds. That works out to a meaningless voltage figure. The problem is, remembering our basic definition of 1 volt, 1 henry, and 1 amp per second, we have to change the di over dt ratio to a basis of 1 second. So if we divide 68 nanoseconds into 1 second, we get 14705,882. 14,705,882 amp per second. That's a tremendous amount of current. But realize this is trying to swing 4/10 of an amp in 68 nanoseconds. On a second basis, that's a tremendous current. And this is why short circuits in systems like this cause fire, smoke, and white flashes. We multiply that fraction, 0.4 over 68 nanoseconds, by a unity fraction of 1470582, and we get 245 microhenry times 5,882,352 amp per second. Now that's not how much current flows in a circuit. Heck, the chassis around the amplifier couldn't pass that much current. It would melt. But that would be the rate per second based on 4/10 of an amp per 60 nanoseconds. Multiply that through and we get 1441 volts across the inductor at the time the tube plate is at 1 kV. Not an expected result. Now that seems to violate Kirchhoff's voltage law, which says the sum of the drops in a series circuit will equal the source. That comes out to be 2441 volts, not 2 kV. Where did the extra come from, and does Kirchhoff's law work or not? It works. It's a law. It can't fail. What we got to remember is that the inductor is also a voltage source. Charge a capacitor, remove it from the circuit, it's a current source. It's stored energy that can become current. Charge an inductor, attempt to separate it from the circuit, and it will make an arc in desperate attempt to continue the current to discharge. That field has become a voltage source. When we try to separate that lead, if we try to cut that inductor lead from the circuit, there will be a very bright white arc where the inductor voltage has suddenly skyrocketed in a desperate attempt to maintain the same current flow. If you've worked with inductors and switches, you know that voltages can be extremely high, tens or hundreds of times, if the switching rate's fast enough. And this is a problem in switch mode power supplies. If we go back to the differential equation and set di dt to infinity, infinity times anything's infinity, so at an infinite current rate, the voltage becomes infinite. Does that happen in the circuit? Yes, it does. At the initial time the current very first starts to flow, the charge in the inductor is 0. The current through it is 0. Voltage across it is 0. Any increment increase in current, no matter how small, is a very small increment in current, which is meaningless. That increment compared to 0 tries to go to infinity because anything divided by 0 is infinity. Calculus can handle that. That's invalid in a calculator, but calculus has ways of dealing with that. The current tries to go very, very high. The highest voltage in the system is 2 kV. Therefore, at the first instant of turn on, that inductor will see the full power supply voltage. So that answers the question as to voltage rating of the inductor. It's got to be rated at the power supply. And with the possibility of going to a larger supply, eventually for a 3-400 or 3-1000 tube, that max can be 4 kV, so that inductor better be rated for 4 or 5 kV. That's a very important consideration. Otherwise, that inductor will turn into smoke. And I did that with one of the inductors in one of my antenna L networks because I used it on the wrong frequency and torched the coil, and it stunk the room up so bad I had to open the windows. That's the mathematical basis for calculating that. But my goal for this amplifier, being that I should have enough engineering knowledge to calculate everything exactly and it ought to work the first time, is that I can't go build this amplifier and test it because it's dangerous. Next video, I'll make a test circuit, use low voltage equipment, and show you how to verify that value. Okay, BYP out.